Hey everybody, this is 1N projectile motion part 2. So it says a rock is thrown horizontally with a speed v from the top of a cliff of height h as shown in the diagram below, basically there. So the very first thing that they want us to do is it says sketch the following graphs of motion of the rock on the axes provided below the diagram to the right. So basically these right here. So they want us to graph the acceleration, the velocity, the position, for both vertical and horizontal. So let's do the horizontal, or excuse me, the vertical acceleration here. So vertically, it's going to have an acceleration of -10 the whole time. All objects, all projectiles have an acceleration of -10. So I'm just going to pick that to be -10, whatever, you could have drawn it right there. But it's going to have a constant vertical acceleration of -10. So what about horizontally? Well, horizontally there is no acceleration for a projectile, and so it should be right there at the 0 mark. All right, so what about velocity? So if it is thrown vertically, or excuse me, horizontally, then it will start with no initial vertical velocity, so we'll start at 0, but then it will start to gain negative velocity, and it will do it at a regular rate. So we need to have a straight diagonal line like that, where the slope of this line would actually be -10 there. What about horizontally here? What's going on with the velocity? Well, the horizontal velocity will never change. It's a constant. So whatever you pick it to be, it doesn't really matter how high up this line you go, but it should be a constant value there. So now let's look at the position here. So what is going on with the position? Well, part of this is, do you call where the rock is thrown, is that the origin, or is the ground the origin? I tend to call where the rock is the origin, so it's going to start right here. And then we're going to accelerate vertically, so we're going to have a curved position graph. And so in the slope should be getting greater and greater and greater because that represents the velocity. So you should have like half of a parabola there. So our velocity, aka our slope, keeps getting greater and greater and greater in the negative direction. Horizontally, as we said, we have a constant velocity, which means we would have a constant slope there. And so some positive value. Now, how steep you make it, that doesn't matter. So just some amount of horizontal velocity right there. So now, in part B, they say a second rock is now thrown at an angle theta above the horizontal at the same speed v, that's important, at the same height h, so that's important, as the rock in part A. On the same set of axes as part A, sketch the graphs for the second rock. If the graphs for part B are different than those for part A, use different colors or different lines to differentiate between them. So create a key so it's easy to tell. Well, I'll just tell you, I'm going to use green for the other lines there. So let's go back to our acceleration graphs. And let's do, well, actually before we do that, let's put something on here to understand before we start to draw those. So let's say our first one is right here, where we threw it straight to the side. So in that case, all of our velocity was initial Vx, so a horizontal velocity in other words, and this would never change sideways. But if we had that same velocity, but we threw it at an angle like that, then what we're going to have is part of this velocity, a component of it will be to the side, let's call that Vx, and then part of this would be vertical, like that, let's call that Vy. And the point is two things here. One is our horizontal velocity will be less than it was before because it's a component of V, it's not all of V. And secondly, now we have an initial positive vertical velocity to deal with. So let's keep those in mind as we draw our graphs for these things. So in terms of acceleration, well, even if you throw it at an angle vertically, you're still going to be accelerating at g, so basically right there on top, same line. And even if you throw it at an angle, there's still not going to be any horizontal acceleration, so right there on top, exactly the same. All right, let's look at the velocity graphs. So this time, what's going to happen? Well, we start with a positive velocity that we throw it up at, but then it starts to come down at the same rate, the same acceleration. So we should have the same slope, the same -10 slope there. So again, how much you start this positive doesn't matter, but it's got to have the same slope as that one and start up here. Now horizontally, what goes on? Well, remember that we just said we will have less horizontal velocity because only a component is Vx now instead of the whole thing. So when we go to draw our horizontal velocity, it's just got to be some lesser amount. It's still going to be constant. It will never change, but it's going to be less than it was before. And so finally, the most difficult ones are the position ones. So now we start going up for a little bit here. And so first we go up, but the whole time we have a negative acceleration, so something like that. So the same basic parabola that we had down here, it's just we start going up first and then we start coming back down. And then horizontally, as we said, we have less horizontal velocity than before, but it is still constant, so we just should have less of a slope than we had before. All right, so next part here, let's look at this. It says in part C, what if instead the second rock is thrown horizontally, but with an initial speed 2v? So would the horizontal distance d between the bottom of the cliff and the place where the rock lands be larger, smaller, or the same as the first rock? Well, to sort of look at that, let's think about two things. And when you have these types of questions on the AP exam, they want you to argue every single point. So even if it seems clear that something is the same, so it doesn't matter, you got to argue that it's the same. So for example, I'll use the third equation. So the position is the initial y velocity times time plus 1/2 times an acceleration of g times t squared. There is no initial y velocity when it's vertical, so that drops out. So now I'm going to rearrange and solve for this t. So t in this case equals the square root of 2y over g. So if they each have the same vertical drop position and the same acceleration due to gravity, then the time is the same and that won't affect it at all. So now let's look horizontally. Horizontally, our position will be our x velocity times our time. So our time is the same, so we can just say this: our position is proportional to our x velocity. So if we have 2 times the x velocity, then we'll go twice as far. So I think that's what most people would guess anyway, but there we argued it. And again, a lot of people will skip this. They think it's obvious, but they want you to make the argument that the time is the same, and since the time is the same, only the velocity will matter. So last part here, then we're going to take that idea, and here they want you to fill in these blanks. Now, in the actual AP test, they would actually expect you to write all of this, but they're sort of guiding you here since it's still the first unit. So it says the blank is the same for both rocks, and so that is, as we argued before right here, the height is the same for both rocks. So the time to fall is also the same. Since both rocks are in the air for the same time, then the rock that is going horizontally faster, which is rock B, goes further. All right, that's it. But I'm going to leave you with one last thing. See if we can answer this in class next time. It says, a ball of mass m is thrown into the air at an angle of 37 degrees above the horizontal. What happens to the magnitude of the ball's vertical acceleration during the total time interval that the ball is in the air? Does A, the acceleration decrease, then increase? Or B, does it decrease and then is constant? C, increases, then decreases? D, increases, then constant? Or E, stays the same? We'll discuss it next time.